Hey guys, welcome back to the Dynamics video series. This video is a continuation of the constant acceleration problems, but for these problems it's going to be more into working with free body diagrams and things like that. So let's get started. So for this problem, it's going to say the unknown mass box is shown initially sliding down the ramp with the speed of 3. If the angle is 10 degrees and the coefficients of friction are both 0.3 and 0.4, how far will it slide? All right, so it looks like we're not given a lot. But for this problem, it's important just always write out what we know. So what do we know? So we're given two coefficients of friction, 0.3 and 0.4, right? So we know from lecture that since they're not initially stated, right, we have two coefficients of friction, coefficient of kinetic friction and coefficient of static friction. So the coefficient of kinetic friction is when this box is moving. The static friction is when this box is at rest, right? And we know the coefficient of kinetic friction is always going to be the lower number of our pair, right? So our kinetic friction is going to have a 0.3 coefficient, and our static is going to have a 0.4 coefficient. Right? And let's label that this is 10 degrees, just so we remember, right? And then that our box is moving down the slope here at a speed of 3. So our velocity here is 3. So that's all we have so far, right? And it's at this point that we got to realize if we're going to need a free body diagram to solve this problem. All right, so let's see. So the question is asking how far will this box slide, right? So friction is acting on this box, it's moving, and then it's going to decelerate to a point where the box is either going to stop or it's going to keep going, and we got to figure out how far will it go. So we got to think, do we need a free body diagram? Well, is it a gimme? Is it telling us that we need a force? Not exactly. It's telling us we need a distance, which isn't a force, so it's not exactly a dead giveaway that we need a free body diagram. But there's clues that we do, right? So it's only giving us a speed, and it wants us to find a distance, right? So a position, right? Just given a velocity. So that is a little tip that we might need a free body diagram. Another one is our degrees of freedom, right? So let's count our degrees of freedom here. You guys should have been doing this in lecture. So our degrees of freedom. How many are those? So what can our box do here? Well, the only thing it can really do is it's not going to jump off the ramp. It can only really go up or down the ramp, which is just one dimension there. So we're only really going to have 1 degree of freedom, right? Because if we stop the box from moving up and down the ramp, let's say we hold it in place, it's not going to do anything else. So our degrees of freedom here is going to be equal to 1, right? And because we're looking for a position, right? We're not really given a position, and we have 1 degree of freedom. We know we're going to need to draw a free body diagram. Free body diagram. All right, so the only thing left is to actually get into it. So let me try my best here to make a box that kind of looks like what we have there. Ooh, the top's a little funny, but more or less, this is going to be the free body diagram for what we have. And then now we can start drawing our forces. So let's look first at action at a distance forces. So that's things like a magnetic force, a gravitational force, stuff that isn't touching the box but is still applying a force to it. We only have one in this case, and it's the most common one that we always see in dynamics. It's going to be the gravitational force, right? So that's always going to be pointing straight down, and it's going to have a magnitude of mass times gravity, mg. Okay, so that's all the action at a distance forces. Now we got to start looking into contact forces. So what is our box touching? Our box is touching the slope, right? At all this point. So what is anything touching? What forces are there? Since the box is fighting gravity, right? It's not falling through the floor. There's going to be a normal force acting on it, so it'll be down here. I'm just going to draw it on the actual dot just to keep my forces nice and neat, right? So we know we have a normal force acting perpendicular to the plane of the slope. Is that it? I think not quite, right? So we still have one other thing, right? If this had no friction on it, it would just keep going forever, right? But we're given coefficients of friction, so we know there's some friction on it. So we know we're going to have a friction force that acts on the bottom of the box, right? And this force is going to be going up the slope, since we know our box is going to be slipping down the slope if it slips. Okay, so let's label this force. So this is going to be our friction force. I'm just going to put an F, and that's going to be equal to something. Since we know in this case we have a velocity, right? We're given that our initial velocity is 3. We know that our box is in motion, so this is going to be using the kinetic friction. So we're going to be equaling our friction force to mu k times our normal force, right? So that's the exact value of our friction force. And then that's all our forces, right? And now we can start summing them. Before we do that, I'm just going to quickly draw these axes, right? Just to make it a little easier when we start talking about the angles. So I'm going to put these here, just perpendicular lines to a lot of these, right? And let me write in some angles here, right? So what is this angle here? Just based on it. If you could see it right away, you will know it's 10, but in case you want to know how we got there, we can come back and look over here at our initial graph, right? So we know that this angle initially was 10, right? So when we do this, since this is a 90-degree angle, right? We know this angle right here has to be 90 plus 10 is 100, so this has to be 80 degrees to get all our angles to match up. And then since we know that when we do this, right, our gravity is acting in this downward direction, and we're looking at this angle right here, you know, since this is also 90 degrees, this angle has to be also 10 degrees, right? So just another interior angle there. So that's how we got that angle. And then let's make our life a lot easier and label our axes in a way that's most convenient. So I'm going to say that going up this way is a positive y, and then going to the right is a positive x. Just to make it easier so that two of our forces are lined up with these axes. Gravity, we can just figure it out at the end. So let's keep going. All right, so now we have all our forces labeled. We can sum them. So let's do the summation of the forces. First, let's do it in the x-plane, or the x-axis. So what forces do we have acting in the x? We have friction, and we have a portion of the gravity force, right? The normal force is acting completely in the y. It's perpendicular to the x, so it's not going to be included for this equation, right? So let's write it out. So we have our friction force, which is mu k n. And then is it positive or negative, right? Is it going in our positive x direction or reverse of our positive x direction? If you look at the arrow, it's going backwards, right? So that's going to be a negative force. And then we also have our gravity, so that's going to be mg, right? And then it's going to be sine or cosine of theta here because it's not completely in the x. So we got to figure that out. So let's see. If we draw this triangle, we know that anything next to our angle is going to be the cosine. And on the opposite side is going to be the sine, right? So is the sine or the cosine in the x direction? It's the sine, right? So our sine here is going to be a sine of 10 degrees, right? And that is acting in the positive x direction, so there's a positive value there. And that's going to be equal to our mass times our acceleration in the x direction. All right, so summation of forces in the y direction next. So let's see what forces we have in the y direction. We have the entire normal component, right? Because it's only in the y, and that's a positive n. So we're going to do a positive n there. And then we have also the gravity component, right, which is negative because it's acting in the opposite of the y positive direction. So that's going to be mg. And since we know in the x direction, mg was sine, in the y direction, it's going to be cosine of 10, right? And this is also equal to the mass times the acceleration in the y. But is there an acceleration in the y, right? So let's look at our picture, right? And imagine this box sliding down the ramp, right? As the box slides, is anything happening in this y direction? Is it going up or is it going down? No, so there's no acceleration in the y direction, right? So we can actually just label this entire side as 0, because mass times our 0 acceleration on the y is going to equal to 0 on that side. Okay, so let's say we have two equations. Let's see how many variables we have. So let's see if we can solve. So we have our normal is unknown, our mass is unknown, and our acceleration in the x is unknown. So we have three variables and two equations, so this is not possible to solve with algebra just yet. But let's see, there's a trick to this problem, and we can do a little bit of manipulation to maybe get one of these variables out. So let's actually take a look at our y equation, right? So we equated the right side of the equation to 0, so we can actually rewrite the equation, right? I'm going to rewrite the y equation here as the normal equals, and I'm going to move this term to the other side, mg cosine of 10, right? And now we have this equation, right? So we can express n anywhere in any of these equations as mg cosine of 10. So what I'm going to do is I'm going to plug this value into this top n up here. I'm going to rewrite it. So let me go ahead and do that. So I'm going to write it down here. So negative mu k, and then where this n was, I'm going to put this mg cosine of theta, no, not theta, 10, which is still theta, right? Plus, and then carry the rest of the equation, mg sine 10 equals, running out of room, mass times our acceleration in the x. Okay, so what can we do now? So with this equation, right, if you notice one thing, what do all of these terms have in common, right? They are all multiplying with an m, with a mass, right? And since all this mass is the same, right, it's just the mass of the box, we can actually divide by m all of these terms and have the equation still work out. And that's going to end up canceling each of these terms, right? So now we can rewrite this equation without the m's. So let's write it again. So now we're going to have mu k, no m, g cosine of 10 plus g sine of 10 equals to our ax, right? And now this equation just got way easier, right? Because we know g, that's just gravity. We know mu k was given in the problem, and we're just looking for a of x here. So let's actually solve for it now. So let's see. So I guess the question actually didn't give us what units we're in. We can just assume it's going to be SI units, right? So what does that mean? We're going to be working with things like meters and kilograms. We're only going to be doing meters here because we only have distances, but just SI units, meters, kilograms, liters, stuff like that. So let's write it out. So our mu k is 0.3, so negative 0.3, times gravity, which in SI unit is 9.8, cosine of 10. Oh, didn't mean to do that. Cosine of 10 plus g, not g, 9.8, right? SI unit, sine of 10 equals ax. Right? And now what you can do here is just plug all these numbers into a calculator and get a value for ax. I did it beforehand, so you guys don't have to wait. And I got that ax was negative 1.19 meters per second squared. Does that negative value make sense? Yes, because we're assuming this box is going to be starting with a certain speed and slowing down towards the end, right, until it eventually stops. So it does make sense for that x acceleration to be a negative number. But that's not the end of our problem. We're looking for not just the acceleration, but how far it'll slide, right? So let's continue. So we had an initial velocity, right? How can we do this? How can we figure out when it'll slide? Let's figure out how long it's going to take for the velocity to go from 3 to 0, right? So we had a initial velocity of 3. Our final velocity, so we want this thing to eventually stop, is going to be 0, right? And we figured out that our acceleration is equal to negative 1.19, right? So we can use our kinematic equation where it says final velocity equals initial velocity plus acceleration times time, right? We have all these variables except time, so we can solve for it. So plugging stuff in, 0 equals 3 plus negative 1.19 times t, and rearrange and solve for t. Again, I already did it beforehand. That's just going to be equal to 2.52 seconds, right? So that's the time we're going to be using. And then now we can do our final step here in solving for our distance, right? So we're going to use our kinematic equation for distance, which goes like this, where the final distance equals the distance initial, right, or x naught, plus v naught, or vi, you can use those interchangeably, times time, plus 1/2 AT squared, right? So let's plug stuff in here. So our x value we're looking for is going to equal to our x naught. We can just treat as 0 because we can just say 0, 0 was our starting point, plus v naught. So our v naught was given as 3. Our time we solved to be 2.52 seconds, plus, and then 1/2 our acceleration, which was negative 1.19, times our time again, 2.52 seconds squared, right? And then this is our final step. We have all our numbers, so we can just plug this into a calculator again. For the last time, I already did this on the other side. So what you should get in the calculator, and the answer for this problem, is the box will stop sliding after 3.78 meters, right? And that'll be our final answer. So it's a little complicated, but as long as you get the steps down of if you need a free body diagram, making sure you draw your forces in the right directions, making sure you sum them in the right directions, picking the easiest axes, and then start working with the equations. That's kind of the steps to success, but that's going to be this problem. Okay, this is going to be the second problem for the video. So this problem asks if a red puck hits with a lower speed so that it hits on a 30-degree... The puck is hitting on a 30-degree plane, sure. And it starts, comes to rest, and then it begins to slide down the slope with no friction. How fast is it going to be moving after it slides 2 meters down the slope? Assume it's long enough so that it's going to remain on the slope. Sure thing. So basically, what this question is, it's simplifying it, is that we have a slope that a puck is on, right? Initially at rest, so this puck is here at rest, and it's going to be sliding down with no friction, right? So just gravity here. We still have that contact force, so it's definitely not a free-for-all problem. But we can start off by analyzing if we should draw a free body diagram, right? So what do we have given? We're given that it's going to slide 2 meters, right? And we want to find out how fast it's moving, right? So it's 1 degree of freedom. We're not given a speed, but we're looking for a speed. That tells us we're definitely going to be needing to use a free body diagram for this problem. So let's go ahead and draw one. I'll try and draw the puck down here. Probably as good as you can draw a puck. I said it was red, but I guess black will work. Alright, and let's draw our forces, right? So this is the puck. Our forces are going to be always, right? Remember gravity, the action at a distance force here. So we have gravity acting downwards. It's going to be mg. What else do we have? Do we have any other action at a distance forces? No, just gravity here. We do have contact forces, right? So we have the normal force from the plane. So the normal force is always going to be going perpendicular to the plane. So we imagine the plane as the bottom of the puck, right? Then our normal force is acting upwards here. Let's make this line a little thicker so it looks better. There we go. All right. And then what else do we have? Do we have a friction force? No, because this thing is sliding without friction. So these are the only 2 forces that are going to be acting at this puck at this moment. So now we can start summing forces. So let's draw these lines just to help us out with some angles. Right? So we have these. Just perpendicular to everything. And let's see where we can get our angles in here. So we know that our theta here is equal to 30 degrees. Right? So we can start plugging degrees in here. Since we know that's 30 degrees, we know this also has to be 30 degrees. Make that a little better. The angle between this axis and the gravity vector, right, is 30 degrees. And then this angle would also be 30 degrees. That won't be very helpful because what we can do here actually is make our life a little easier by making the axis like this. So our acceleration is only going to be in x direction. And then we have no acceleration in the y direction because the puck is going to stay on the surface of the slope. Right? So let's sum our forces here in the x and the y. So I'm going to sum up over here at the top. So sum of the forces. Let's see. So in the x direction, what do we have? We have just the gravity, right? Or a portion of the gravity. So we have mg, right? And then we got to figure out if this is sine or cosine, right? So we know that the side adjacent is going to be the cosine to that angle, and the sine opposite, so this over here, the opposite side, is going to be the sine. So is the x on the sine or the cosine? Which line is it parallel to? It's parallel to the sine, so this is going to be mg sine of 30, right? and then that's the only force in the x direction, so that's a positive number, right? It's with the x, and that's going to be equal to our mass times our acceleration in the x. Okay, so let's do our y component just to finish it off. So y is going to be our normal forces completely in the positive y, so we can add that initially. And then we have gravity, so mg, right? Since our x direction was sine, our y direction is going to be cosine, so cosine of 30. And then it's moving down, right? Gravity is pulling down in the y direction, so it's going to be minus, right? And that's going to equal to our mass times our acceleration in the y. Since we know this thing is going to be staying on the slope, it's not going to be doing any jumps, then our acceleration in the y is just going to be 0. So mass times our 0 acceleration in the y, this whole side also becomes 0, right? That was useful in the last problem. It's not going to be very useful in this one because we don't have no friction to replace the normal force with, right? So this y equation isn't going to help us very much, but it's good practice to get it done. So let's use CRx, so our top equation. We see that both of these terms up here, right? One term on each side, they both have an m in it, so we can actually cancel out both of these m's, right? Since they're the same on both sides, and then rewrite that equation here. So let's see, we have that g times the sine of 30 equals our acceleration in the x. All right, so we can just get our acceleration right away, since g is just a number and sine of 30 is just a number. So let's assume we're using SI units. That's the common assumption, unless they tell you, oh wait, actually we don't have to assume because they told us meters. Perfect, so we know we're in SI units. So 9.8 times the sine of 30, right, equals the acceleration in the x. If you punch that into a calculator, we pull it up, you would get that the acceleration in the x is going to be equal to 4.9. And then let's put the unit meters per second squared. Perfect. So let's continue. So what are we looking for? We're looking for how fast this thing's going to be moving after it goes 2 meters down the slope, right? So we're given a couple things. We're given that the x is going to be 2 meters. Our v initial, right, which is our v naught. Our initial started at rest is going to be 0. We want to find vf, right? That's what we're looking for, our v final after it goes 2 meters. And then just arbitrarily, we can treat our initial x value as 0, just right where it landed. So let's analyze this. So we can use actually our x kinematic equation for position, where we know that x, right, or an x distance is equal to the initial x value, right, or x naught, plus the velocity initial times the time, or velocity naught times time, plus 1/2 acceleration times time squared, right? So we can treat this x value as 2, right, because that's how far we want to go. And we can solve for time in this equation. Because our x value initially was 0, we can treat it as where we landed as 0, 0. Our initial velocity, since we began at rest, was also 0. So 0 times t is also 0. And then plus, we do have an acceleration, right? We just solved for it. Our acceleration in that x direction was 4.9 times t squared. From here, it's just doing a little bit of algebra to solve for t. I went ahead and did it for you before I started the video, and it happened that t is equal to 0.9 seconds. All right, so that's our time. That's how long it's going to take for us to travel 2 meters. I'm accelerating at 4.9. And now we can solve for our final velocity, right? So we have this second equation where we know a final velocity is equal to an initial velocity plus the acceleration times time. So we can plug values in here, right? So our final velocity is what we're looking for. So Vf is equal to our initial velocity was 0 plus the acceleration, which was 4.9, times our time, which we solved to be 0.9 seconds. And then doing that multiplication, I got that my Vf is going to be equal to 4.42. Right? And then that's it. That's what the question was asking for. So I'm going to go ahead and underline this to denote my final answer. This one was a little more simple than the last problem, but still, it's important to know how to do these for your exam. You might see one, just a box or a puck sliding down either with or without friction, and just know how to sum these forces, manipulate these equations, and use your kinematic equations to get what you want. But that's the end of this video. Bye.